Well, good evening, everybody. I'm Samuel Singer, founder and executive director of Wyoming Stargazing, and welcome to this month's episode of the World Above the Tetons speaker series. We're excited to have Dr. Scott Bailey here from Virginia Tech, and he's got some fun information to share with us about doing astronomy on a rocket. Definitely remember to stick around after Scott's talk for some door prizes. Thank you to all of you for being here, and thanks so much to all of our sponsors for making these events happen. Scott, we're all yours.
Sure. I'm going to share the screen now. I really appreciate you guys letting me do this, and appreciate you coming to listen. You're going to see quite easily as I talk about this that I enjoy what I do, and I enjoy talking about what I do too. I hope I can make it interesting for all of you, and I hope you'll be willing to ask questions as we go. I'm not a formal speaker. I like it to keep it a casual discussion, and especially if you know, I get off and get too detailed or whatever, just stop me and say whatever you want. Let's make this as much fun for everybody as we can do. I'm going to tell you about an experiment to sort of do astronomy from a rocket, and I'll tell you what that's all about. This is a NASA project to study a particular chemical in the Earth's upper atmosphere, and I'll explain, you know, the background of what we're doing. But before I get too far into it, I wanted to show a list of names. I'm not going to talk about everybody, but you're going to get the sense as I go through this talk and talk about things we've done. There's a lot of people involved. A lot of things have to come together to get this to work, and I won't be able to talk about everybody's role, but there's a lot of people who made hugely important contributions, and I'm not even listing everybody. I'm listing a few people and their team, right? There's many people who participated in this and had a big role. So I'm just a guy who gets to represent it, but please know that there's a lot of people who helped with this and were important. A couple names I'll probably mention as I go are Bill and Justin. Bill is out there at University of Colorado with Cora, whose voice you heard a little while ago. Justin Carsons is here with me. I mentioned just their two names because we've all three been together since the beginning. We've been working on this for 14 years. Just finally got it to work this past January. And so there's been up and downs that I'll tell you about, and we kind of enjoyed that roller coaster together, you know, at every aspect. And we were together in the control room during the launches for each. And I'll tell you about some roles as we go, but they've been important to it, and we've been doing all of this together. This is a picture of our rocket experiment there. I can't actually show you a picture of the assembled rocket with the motors on it. We launch out of Poker Flat, Alaska, which is 35 miles north of Fairbanks. And when they put it all together and put the motors with all the telescope section and the radio and the pointing system and all that, they have to do that in sort of secrecy because it's a little bit dangerous. You know, somebody lights a cigarette, you know, something really bad can happen. So they don't let anybody in there, especially not a scientist, right? They keep everybody out, so you can't get a picture. But once they put it together, it's going to be in minus 40 degree Alaska. This is a winter. We launched January in this past year, so it's minus 40 out there. You see us all dressed for it. So the rocket experiment can't take that. The electronics, nothing likes that. So they seal it up in styrofoam and then run warm gas over top of it to keep it warm. And there's a building they can roll over top of this. This launcher folds down and they can move a building over top of it and cover it. But you got to keep it warm the whole time it's out there. So you'll never actually see a picture of people standing next to the rocket. It doesn't happen up there. If we launch from somewhere warm, we can do it, but we can't do it there. But I'll show you some cool pictures along the way. Let me start with some of the science. And so this relates to the Earth's aurora. And if many of you are there in near Jackson, Wyoming, you probably get to see an aurora like this at least every now and then. Up in Alaska where we were, they're more common. Beautiful sight, very spectacular nighttime display. Some of them are just phenomenal. It doesn't matter how cold it is, you will stand there and just watch them. They're so spectacular. But there's more to it than just the glow. There's other things happening. The glow is part of a chemical reactions that are occurring, and those chemical reactions do interesting things. And it's that chain of events that starts with these glows that I want to talk about. And just to remind you what's really going on. You know, the particles that cause that glow start with the sun, and they're coming out away from the sun in what's called the solar wind. The solar wind reaches the Earth, which is one giant magnet. And so some of those particles flow along the Earth's magnetic field, go way out to the back, and then go way far away from the sun, but are eventually pulled back in and enter and hit the Earth at the polar region. Some of those particles do find their way across the magnetic field line. That's more difficult, but it does happen. But the same thing eventually happens. The magnetic field brings them to the polar regions, in South Pole and the North Pole. They don't generally hit lower latitudes, which is why you see a few aurora in Jackson, Wyoming, virtually none in Virginia, and a lot up in Alaska or northern latitudes. But it's energetic particles. There's lots of energy in those particles. They come in, they stream into the Earth's upper atmosphere in the polar regions, and they have lots of energy. And one of the things they can do is when they strike a molecule, so this E star is meant to represent energetic particles, when they hit a molecule such as nitrogen, molecular nitrogen, which is in the air, it breaks it apart, right? This molecular nitrogen becomes atomic nitrogen. That is no simple trick. It doesn't happen often in the atmosphere at all, but when you have these energetic particles come in, it does. And those, or some of those atomic nitrogens, can react with oxygen, the same oxygen we breathe, and form a chemical called nitric oxide. I've spent a big part of my career trying to understand the formation, the destruction, and just the overall behavior of this molecule in the Earth's atmosphere. And I admit I'm simplifying what happens by a fair amount, right? To really explain nitric oxide takes more chemical reactions, but this is the gist of it. All right, energetic electrons break up N2, the N's work with O2 to make nitric oxide. And then the typical way you lose nitric oxide is when sunlight shines on the nitric oxide. H nu is meant to represent solar light, reacts with nitric oxide, breaks it up. In fact, it breaks it up in such a way that makes another atomic nitrogen, which when that reacts with nitric oxide, destroys it, and you get the N2 formed again. So the aurora creates nitric oxide, sunlight destroys it. Interesting things happen. So go back to this diagram on the left, and you have the aurora creating nitric oxide. When you go into the high latitudes and this happens, this again, you know, you have long dark winters. Above a certain latitude, the whole winter is completely dark. So this sunlight destroying NO doesn't happen, at least doesn't happen nearly as much, or eventually at some latitudes it goes to zero. So now the nitric oxide is created, and what does it do? It's hanging in the atmosphere, it's up at the auroral altitude, which is like 120 kilometers. Without sunlight to destroy it, there's time to work its way downward. And that can be through winds, that can be through processes called diffusion, but it can find its way down. If that happens, nitric oxide, when it's in the presence of ozone, will destroy ozone. And it will destroy ozone in such a way that the nitric oxide survives. That's called a catalytic reaction. So it's a very efficient destroyer of ozone. Now, this is not the cause of the ozone hole, but it is the cause of a certain amount of destruction of ozone, enough that probably changes the circulation of the Earth's upper atmosphere. And if we spend more time talking about the science, that there may even potentially be a link with climate at the surface because of the disruption of the winds at the high altitudes. I don't want to get into that. You know, my goal here is to try and understand the NO. How is it distributed in altitude in this polar night? You know, how much, to what magnitude does it grow to in this polar night? And is there any evidence of it moving downward? This polar night, where there's primarily darkness for a period of months, we don't have good ways to observe that. We have very little in the way of observations of that. And so there's a lot we don't understand. And this is what I want to try and understand. This is a figure from 20 years ago now, where a satellite mission called SNOWY observed nitric oxide. So this is just sort of a map, latitude on the y-axis and time on the x-axis. And the bright colors signify how much nitric oxide there is. And you see, as you get away from the equator and head to higher latitudes, you see more and more nitric oxide. And if you look near winter, right, you see very large amounts of nitric oxide. But you notice it's dark at the highest latitudes in winter. We can't see because there's no sunlight. And you need the sunlight to do most observations. Most of our techniques, not all, but most of them, use sunlight as a way to study the Earth's atmosphere. So you take away the sunlight, we can't see anything. So we can tell the abundances of nitric oxide are large, but what do they get to in here? And to what altitude do they settle? We don't know. Another experiment called SOFIE, which is, by the way, led by one of your members, Mark Hervig, and his wife Carlin, as a member of they're members of your group. This also uses the sun. It kind of uses the sun as a light bulb and looks through the atmosphere, and by how that sunlight is absorbed, backs out a concentration of nitric oxide. And so here's altitude in the y-axis and time on the x-axis. And you can see when you get to the winters, there's large amounts of nitric oxide, not much in the summer. And you can see that in the winter, it tends to go to a lower altitude, sometimes spectacularly low altitude, but most winters less so. This is the same thing. This is a measurement that's up at high latitudes, not in the polar night, but near the polar night. So there's still some sunlight left. So the nitric oxide has time to descend lower in altitude. But again, how much lower can it go when it's inside the polar night? These big dramatic events of descent are when a certain wind pattern sets up after a meteorological event. You guys have heard of the polar vortex, right? Its behavior and what it does to climate. When we have stratospheric warmings that affect that polar vortex, the winds can set up in such a way to just pull that nitric oxide right down. Very dramatic. And again, this is still in the latitude region where there is sunlight shining to some degree. So I don't imagine what it was like inside the polar night where there was no sunlight, and there could be lots more NO to be pulled down, but we couldn't see that. We haven't been able to see that yet. And I want to say you should be impressed that such a system like this can form, right? This descent here that's happening over a few weeks, yeah, it's going down 30 kilometers. You say 30 kilometers, that's nothing, right? I could ride my bike 30 kilometers. But 30 kilometers in altitude, right? The atmosphere changes pressure roughly about every 10 kilometers or so in altitude. So this nitric oxide is traversing factors of 100 or 1,000 in pressure to get down. Now that's happening because of a wind, so it's not like it's going through a wall necessarily, but it's a big distance. For atmospheric process, this is a huge descent event. And again, what is it doing in the polar night? We've never been able to observe that well, and this is what I'm trying to answer, is what's going on in the polar night. I did not try to launch the rocket during an event like this, but I did try and launch it during an event like this to see if we can understand what's going on. And here's just one of those, what I would call a typical winter up close. Again, time on the x-axis, except now it's days relative to winter solstice, so that's December 21st is day 0, and altitude on the y-axis. And you see the NO is variable in time. That's because the aurora is variable time. Some days you get a big one, some days you get a small one. So when you see a lot of NO produced, that was because it was a big aurora. And you can imagine this is coming up to winter solstice, so the length of the day is getting shorter and shorter as you approach winter solstice. And you see when the length of the day is shorter, the NO goes down lower. And there's probably other things going on. But you know, more time for the NO to survive, the lower the altitude we see it. But again, we've only really observed NO to any significant degree at locations where there was sunlight. We're using sunlight to make this measurement. What I want to do is measure without the sunlight and see what's going on in the polar night. And just one more figure, this is something else we don't have good observations are, but if we look at the NO density, and I'm just kind of using a nickname NOx, which really means NO plus atomic nitrogen, but it's basically nitric oxide. And here are the color. This is time on the x-axis, altitude on the y, and color represents increases in NO. So red is very positive increase in NO. And here's ozone in the same times and same locations. And here it's decreases, right? So the colors are telling you about loss of NO. And you can see, at least qualitatively, when we have more NO, we have more loss of ozone. It's not a perfect correlation, but it's a very good correlation. And we think if we had better observations, we would see this in much greater detail. But this whole area that I'm talking to you about is an area where we're observation limited. Let me now start to talk about making the measurement. What I want to do is measure nitric oxide, measure its distribution with altitude in the polar winter, in locations where there is no sunlight. And what we do is, as I said, we very often use the sun as a light bulb, and then look at sunlight as it goes through the atmosphere and look at how that's absorbed to measure the concentration of NO. I'm going to do the same thing, but the star is a light bulb. So this way I can do it at night, right? So we pick a star, we launch the rocket, we point the rocket. Actually, the rocket has a telescope coming out the back. If you think of the nose cone as the front, look out the back at the star, and as the rocket goes up and down, we stay focused on the star, and then we look at the altitude profile of the brightness of the star, and where we see lots of attenuation of the starlight, if we're looking at the right color, wavelengths where NO absorbs, right, we can back out the concentration of nitric oxide. It's a little complicated because I'm looking through lots of altitudes. So you have to take that into account. You could imagine that I could do this experiment, launch the rocket straight up and have the star up here, and then look as I go up and as I come back down. That would be a really straightforward way to do it. But I'm looking through much less atmosphere when I do that. When you look up straight, right, that's a little bit of atmosphere. When you look through all this, you see a lot. And so I get way more absorption of the starlight when I look in this geometry. The price I pay is I have to do some sort of technique to account for the fact that I'm looking through multiple altitudes. I have to do some sort of mathematical technique to interpret the data. But that's a small problem in comparison to getting a much better signal by doing it this way. In fact, if I try to do it this way, I would need a telescope, essentially the Hubble Space Telescope, to make this experiment work, right? I have to do it this way. And then you have to ask yourself, if you're going to do it this way, you know you're going to use a star, you know you want to look at the atmosphere tangentially to get a lot of absorption. How do you design the best mission to do that? Well, you're on a rocket. This is a missile, right? They put a solid fuel motor on it, right? You have your telescope, you strap a motor on the back and you launch it up, right? I can't control the position of the star, right? I can't drive this thing around like the Millennium Falcon, right? I can just have the rocket go up and come down like a missile. I can make the rocket heavy or less heavy in such a way that I control the altitude that the rocket goes to, but I have to plan that ahead. And I can control the angle in flight to whatever I want. And of course, I want to point at the star. But I can choose what time I launch. So what time I launch, the star is high in the sky or low in the sky. Remember, I said I could pick it straight overhead if I wanted, but I don't want that. I want it to be actually very near the Earth, right? So that I can look at the atmosphere sideways like this and get lots of absorption. But I could still have it a little higher and then make my rocket less tilted, or I could have the star a little lower and make the rocket more tilted. And what makes me decide one versus the other? Well, when a rocket goes up and reaches its apogee altitude, it's going to go to zero velocity. And then it falls. There's no motor. It's like dropping a rock. And the rocket's going to come down. You always get your best observations on the down leg because there's no accelerations other than gravity. You've already had time for the gas to move out of the rocket. Everything is set up and aligned. So you're essentially releasing it from zero and letting it drop through the atmosphere as it goes. And it's going to accelerate due to gravity, right? It's going to start off very slow and then increase in speed. Well, the altitudes I'm most interested in are the altitudes where nitric oxide is 100 kilometers, and I'm going to see NO absorption. I want the rocket to be moving as slow as possible when that happens so that I get more time to be looking at the altitudes I'm interested in. But I need to go to an altitude where I can be confident there's no nitric oxide along the path because I need to know the brightness of the star when there's nothing along the path. So I can pick the apogee altitude, and I can pick essentially what time I launch so that the star is in exactly the location I want it to be in so that I get exactly the angle I want that favors my geometry and my time looking at the altitude of interest. So you put all that together, we got to an apogee of 260 kilometers and an angle of just about 100 degrees. Call this a zenith angle. If you go from the center of the Earth up to the rocket and then look at the rocket to the star, and that angle in between, 100 degrees optimizes everything I want. Okay, from a timing perspective. And so that means I have to launch when the star is at such a place that when the rocket is up here making observations, right, this angle is 100 degrees. That's how I pick my launch time. And everybody on the team loved it when I told them that was 4:40 a.m. right? You have to be at a rocket launch about 8 hours before you actually shoot. So that meant everybody was up all night. And so I was very popular with that, but it does turn out to optimize it. And just to tell you a little more about it, so we're launching out of Poker Flat, Alaska. That's a standard NASA range where they do sounding rockets out of. They launch maybe 1 to 4 rockets per year out of here. NASA launches about 15 to 20 of these total per year, but only a handful up in Alaska each year. This year we were the only ones to go. We have to launch north because that's a corridor where there's minimal people living there, and so they feel safe flying a missile right over top of everybody. Although I'll tell you one quick story. One night where we launched, and we had been there a while, and I told my wife, we're definitely shooting tonight. It's going to happen. I'll be able to come home tomorrow night or the next night. And then some little town in here, 2 guys got in a knife fight and hurt each other. So from Fairbanks, they had to send a medicovac plane up in the launch trajectory to go evacuate those guys out. And they said, we can do that in 20 minutes. Don't worry, we're not going to interfere with our launch. But famous last words, we had to scrub the launch while they pulled those 2 guys out, and thankfully they lived. But anyway, we're flying in this trajectory, and I want to look up in the polar night. So this over here to the right is the same figure. This is Alaska here, looking into the polar night. This outer circle is the 67 degrees latitude that forms what we call the polar region. And so 24-hour darkness anywhere in that circle on winter solstice. And this inner circle is the region of the atmosphere where it's been dark for more than 2 months when we launched on January 20th. So I want to make an observation in here. And so here's the rocket trajectory, but we're looking at a star, right? And so where we're actually making the observation in the atmosphere, where we're getting this tangential, right, crossing through the atmosphere, that's here, right, or here, right? It's about 1,000 kilometers ahead of the rocket because we're looking down through the atmosphere way ahead of us. And that's where we get this favorable geometry, what we call the tangent point. Okay? So you can imagine, how do I pick a star to do this? I need a star that has a zenith angle of about 100 degrees and is oriented along this way when I'm launching, right? I can't have a star that's south, right, or east or west. It has to be north, right? And the interesting thing about that, for some of you who go out and do astronomy, is that's actually a declination of 15 degrees. It's an equatorial star, right? It's overhead if you're right down near the equator, right? If you're up in Alaska, I want it near the horizon, right? So it's a low declination star that gives me this geometry that's not intuitive, but that's how it works. And so we pick that star. The other consideration for the star is that it's bright in the UV, right? Our experiment works at 215 nanometers. So I need something that's bright in the UV and gives me a zenith angle that does exactly what I want it. In the visible, this is a magnitude 2.9, so not particularly special in terms of a bright star. But in terms of the UV, of all the stars near the equator, this is about the 6th brightest in the sky. And so that was important for us. And it has that geometry that we need most of January, but especially the 21st through the 31st, which was right when we wanted to launch. And it meant we had to launch near 4:30 in the morning. Just to plot what that looks like, this is the zenith angle. So remember, low values mean the star is higher in the sky, so the star comes down to some minimum. This is plotted in terms of time since midnight, so it's about 300 minutes past midnight, a little before 5 a.m. That's where it gets almost at 100, not quite to where I want it, but close, and then starts to go away. So I want to have some launch, you know, up here where the zenith angle is as close to 100 degrees as possible. And if I look at that in a way that's important to me, right, how much time do I get observing an altitude range, in this case 80 to 90 kilometers, right, that peaks at the same time the zenith angle approaches this 100 degrees. So what time do I want to launch? It's in here. Here's where I maximize my time looking at the altitudes I'm interested in. It's not a huge loss if I launch an hour earlier or an hour later, but if I launch too early, there's a critical angle where the star never gets to a position where I'm even able to see 80 to 90 kilometers, right? So I don't want to launch too early. I have to launch somewhere in here. And it's 4:30 in the morning, roughly, and it optimizes my observation, basically. Other considerations, I'm not going to take a lot of time. I need to know where the sun is and the moon is if the moon is in the field of view, this is all going to be, it's not going to work. You know, that'll be toast. Got to worry about all that. But that's basically the mission planning. Let me switch gears and talk about the instrumentation a little bit. We use what's called a classic UV spectrograph. So maybe some of you are familiar with spectroscopy, have an interest in astronomy, but just to say it, the job of a spectrograph is to sort the light out by color, by wavelength. And we need a very specific wavelength, and they're 215 nanometers, and we have a very narrow region of wavelength we're looking in, just 4 nanometers. So this would be considered a high resolution spectrograph. The light comes in from a telescope. It's focused to an inch of this spectrograph. It's collected by a parabolic mirror here. This is about 4 inches in diameter. And then what's called a grating is here. That reflects the light, but it reflects the light at different angles depending on the wavelength of the light. So every wavelength gets dispersed or reflected at a different angle. A second parabolic mirror to collect that, and that focuses the light from this grating onto our sensor, our detector. So some of you, if you're doing astronomy with a telescope and you have some sort of camera at the focus of that, there's some sort of chip like what's in your telescopes in here. Here it's optimized for UV, and it's meant for very dark levels, low signals, because we don't get that many photons, really due to the high resolution nature of it. We're looking at such a small wavelength interval. But that's the gist of what goes on. We have a telescope that's in front. I probably have other versions of this picture, right, that feeds that. In fact, yeah, here's a picture of the telescope. It's about 48 inches long. You see it inside the skin that we use to fly. That's about a 1/4 inch of aluminum between the outside atmosphere and the inside of the payload. Our mirror, our primary mirror in here is 18 inches diameter. For a rocket, that's very large. You can't fly that in a standard rocket diameter. We have to fly what's called a bulbous payload, an extra wide payload to be able to do this. That's about as big of a mirror as you can get into this type of NASA mission. Anything else, and now you're talking satellites and very expensive. This is so 18-inch diameter. It's got a 3-meter effective focal length, and that whole thing is about 48 inches wide. What we do is put right inside, you can see this holder there. We block out the center of the mirror. It's a Cassegrain, so it has a hole in the back end anyway, but we block out this part of it, and we put a star tracker inside there, right there. The star tracker, if you're familiar with these devices, looks at the pattern of the stars and then figures out where in the sky you're looking. It can do that to very small fractions of a degree, arc seconds, 1/3600th of a degree. It's very good at doing this. This is a particular device built at the University of Wisconsin. This is a technique that NASA has down well. They've been doing this for 40 years. They can point you at a star to a really high precision using a device like this. And so we just put that at the center of our payload. This is our primary pointing method. And then how does it all go together? There's 3 sections. So the spectrograph is in the center. There's some electronics to get our data out. And you see the payload shrinking in diameter, because again, this is all out here is what we call bulbous. It's large. We have the telescope on one end. The motors actually go here, and the motors drop off, and then we open a door so the telescope is exposed to the sky. And then back here, we mount all the NASA sections. They provide the radio, the pointing system, the batteries, and thankfully the parachute, so that we can get all this back. But this section is the part we built here at Virginia Tech and University of Colorado, and a little bit from Utah State University. And this part comes in at about 316 pounds. Now, I want to talk about the pointing a little bit. I told you there's a very good star tracker in here, and it is. You know, NASA can point this rocket to arc seconds, 1/3600th of a degree, which is much better than we need. We need about arc minutes, so 1/60th of a degree. But when NASA typically does this, right, they're with astronomers, and the astronomers want to look up, right? There's no self-respecting astronomer when it looks down at the Earth, right? That's not what they do. When you look down, you have a couple things going on. One, the darn Earth is in your field of view. You get nothing on half your image. We're up in the polar regions, and we like the aurora, and the aurora is now in the field of view of your star tracker. And then something that's uniquely Alaska, when we launch a rocket like this, the FAA shuts everything down for 100 miles, right? There's roadblocks. The airports can't do anything. That's all totally shut down. But it's Alaska, and there's one airport for about every 5 square miles, and some people who just don't pay attention to the rules. So I have video using star trackers in Alaska, and you watch the video, and you just see a plane fly right through the field of view, right in the middle of the night, 4:30 in the morning, right? Probably they came out to see the rocket launch from the plane. And so the star tracker is not going to work in that kind of circumstance. So we can use the star tracker, when a rocket first goes up, and before we're making our observations, we can use it to check the point of the rocket. And we do that. We point at a star that we're not interested in to get a lock on the pointing and make sure we do it real well and get set. But we cannot use it for the star that we're interested in, because that's way down close to the Earth. You're looking through the aurora. You got these guys flying around, and you have the Earth blocking the field of view, all these problems. And probably we could design a system that accounted for all that, but who's going to be the guinea pig to go and fly that and see maybe it'll work and maybe it won't, right? So what we do is we do go up, we lock on a star, what we call our guide star, to get it set up. And then we maneuver down using a gyro. A gyro is the same sort of device that's in your cell phone that figures out your orientation when you flip it around. And it's nowhere near as accurate as a star tracker. It's just basically sensing the motion. And it does a pretty good job, but it has an uncertainty that's bigger than the precision we need, right? It's probably good to within 10 arc minutes, and we need a few arc minutes pointing on a star. So we can't rely on that. And so we use a trick, right? This is uniquely rocket. You wouldn't do this on an expensive NASA satellite, right? Remember, the telescope is feeding into the spectrograph. The spectrograph has an entrance here, and here's the gradient, there's a mirror over here and all that. But it comes in and focuses to a point, and we have an aperture here, right? There's an entrance to the instrument, right? This is all normally covered in flight, and there's an entrance here. Well, if the telescope is not pointed perfectly at the star, if there's a 10 arc minute error or something, the light will still focus, but it'll focus on this entrance aperture. It just won't go in the instrument. It'll be in there somewhere, but it won't be where we need it to be. And so we'll know it's not pointed right because we won't see any light in our spectrograph. What we do is we put a TV camera in here, and a mirror here and a mirror here. So the TV camera is effectively looking at the entrance to that instrument. And so if we're misaligned, we can actually see the starlight on the entrance to the instrument, and we see it in the TV. And we literally have a guy with a system there that's not exactly a joystick, but just like a joystick. And if he sees any light in his system, he joysticks the rocket over there to put the light into the hole to get us in the spectrograph. And that's literally how we do it. Now, he's got to do that in under a minute for us to get all the observations we need, because all of this, everything in the experiment happens in just 5 minutes. So you have to do this fast. But no joke, this is how we do it, right? And so I pick a guy who's good at Xbox, right, to do this part of the rocket. And, those guys are used to doing it at 4:30 in the morning, too, so it's not too big of a deal. His name's Justin. And I want to show you, you guys are, do something like this. The TV camera we have there, for a long time, we used one called a Zybion. Total piece of crap. This one we used on this last launch by Photonis, a Nocturne. This is a really good, rugged thing. If you're buying sensors for your telescopes, I would totally recommend this. And this is a picture of us testing it. So this is the TV camera, right? This is us on a screen looking at it, and you see there's a dot when a star that's right outside our building here where I am, right? And we're slightly misaligned, and so this is what we see. And this is our sophisticated NASA drawing of where our field of view of the instrument is. We need to get it into this hole. And so we see something like this in flight and then just drive this star into the hole. That's how we do it. This is us doing this out in the parking lot here at Virginia Tech. That's our rocket experiment right there. It's being held up by a lift that's meant to be holding up a car engine. We do have a gimbal right here, but there's no motor or anything like that. It's nothing fancy. It's basically controlled by, enthusiastic graduate students. Hold it in with the lift and with this gimbal and then moving around until we can see the star. I'm sure what you guys do is much fancier than this, but this is what we do. And this is a crucial test, right? We can put it in the lab, and we have great collimators, great optics to test this with, but you can fool yourself in a lab as to whether you're really in focus. When you go out there and you shine a star in, that's how you know you're in focus. You cannot, right? You can't make a star enter your telescope out of focus, right? You know you have a point source when you point that star in. So if we see this, we know all the optics along the way is working. And even more important than that, we get a sense of how bright the star is on this TV camera. Because again, we got to do this at 4:30 in the morning. We don't get to do too many tests like this. It's very hard. And so we do it just a couple times. We have to adjust ourselves to what this is going to look like, so that when we get in space, what do we do? There's 5 of those, right? We got to make sure it's the right thing, and we guide it into the star. And we want to know that that TV camera is sensitive enough to see this. So this is a test, a very important test, and took a lot of work by a lot of people, but you can see the smiling faces when we got it to work and verified we were in focus. But I want to explain that to you so you see how to do it. And I mentioned at the beginning that there's been some heartbreak on this payload. We flew this the first time in January 2011. I told you we've been at this 14 years. So the first flight was 2011. And something happened that I don't think any smart engineer could have predicted. So go back to a picture like this. This is our rocket. There's an aluminum skin around all this. We're working at 215 nanometers. That light travels through the air, at least for short distances, in the lab. There was no reason to pump the air out. We could test this in air, no problem. We put holes in the side of the rocket so that when the rocket went up, the air went out, so there was a good transition to vacuum of space. That's totally standard, done on lots of rockets. Most of the rockets I had done before this work that way. But an interesting thing happens if you're evacuating the payload back here. So as the rocket is going up, all the air is flowing to the back of the payload and out the holes, right? So in this figure, where did I go? I apologize. In this figure, the air is coming through this way and then comes out the rocket. But eventually, when we expose ourselves to space, we're opening a big door over here. So instead of these little holes, what air is left now turns around and goes this way and goes out the other end of the rocket. And as you can imagine, if you ever worked with a vacuum system, the first thing that goes is the clean stuff, the nitrogen and the oxygen that's in the air, then maybe the water, and then it's all the dirty stuff, the big hydrocarbons, complicated molecules. They're big and they're slow. They go out last. So first they're heading this way, then they're heading that way, and it's the dirty stuff at the end. And what happened, took us a while to figure this out. I'm sorry, I'm having trouble with this. What happened was, as the air flowed this way and left the payload, this relay mirror here, part of this mirror system for the TV camera, gets cold because air is flowing by it. It's like a bridge. You have air flowing above and below it, cools it off. And then when we turn the air around, all that messy, dirty stuff that was remaining flowed back this way. It's like your glasses when you walk outside. Everything condenses on the coldest surface. So all the stuff that flowed around, a bunch of dirty stuff got onto this mirror. And if you look at this, this is the mirror after flight. It was covered with about a 16th inch of jelly, right? And what happened was something wasn't cleaned properly. We think it was the rocket skin itself, but this is not something we've ever settled. Very, very small amounts of oil that were still there and shouldn't have been come out when you put the rocket into vacuum when it's out there in space. And because of this flow I just talked about and the cooling of the mirror, it all collected on that one mirror. So when we got into space and we did the TV camera trick, we saw gray. And then we tried all kinds of things. We had plans for what if the TV camera didn't work. We never got the star into the field of view. We lost the whole flight. And we didn't know what really happened until we got it back and we opened it up and saw this mirror and then figured out the whole path. So, this was a great plan. We still use it, but it has this fault. When the mirror is coated, it doesn't work. You couldn't focus. So we did it again in 2017. And this time we pumped the payload out first. So we got rid of those holes, put a vacuum system onto the rocket, and then pumped it out before flight. That was interesting because, as you saw, the rocket the launcher folds down, you mount the rocket to it, and then you lift it up. So we had twice where we were bringing the rocket up and down and forgot to unplug the vacuum system. And so had to run down there and stop the people and pull the vacuum system off. And both times we froze it because we were doing that out in -40. So I've now learned how to defrost a vacuum system. But anyway, I wanted to tell you about some of the trials and tribulations. I wanted to show you, this is the area where Justin works during flight. He's doing the pointing. So he's got the TV that I showed you and our, very precise locations of the aperture that we need to get into and the shape of the aperture where the starlight might be on. So he sees starlight, he moves it in. He's got a zoom up on that. He's got the arrows that tell him, right, how to joystick it if he sees a star in a certain position. And he also looks at the position in the star tracker where the star is in that. So he's got all these videos to look at, and when he sees a misalignment, he corrects it. I say with a joystick, it's not exactly that, but it's close to that. And I should just point out, those of you who know Justin, who works with me, the guy's brilliant. Most people do this. Some people do that. Being able to use the star tracker was a new invention that Justin did himself. And it sounds like something that should be easy, but it's not. And he had to build a whole system to make this work. And if I could give a talk just on this, I would explain to you what went in it. But he's a real innovator with this kind of thing. Lots of astronomers do what I'm talking about, but I think we came up with a better way. Anyway, that's an aside. Other testing we do is out at Wallops Flight Facility. This is the rocket all put together. Our sections are over here, the wider sections, and all the NASA, the pointing, the batteries, all that sort of stuff. We do lots of tests, many of them functional to make sure it works, but we also do a vibration test where we put it on a table like this and then basically shake it the way it's going to happen in flight, very strong vibrations that simulate what's going to happen during launch. And then you sit there and you listen for the screws, right, to see if you hear this, and when you do, your heart skips a beat because that meant something wasn't tightened properly. And, sometimes they break, and I've seen this happen. It's incredibly depressing, a bolt break or something like that. But usually, if you're well prepared, this goes very straightforward. You have the instrument on while this happens so that you can make sure that the instrument works throughout that vibration, that you don't lose communication with it or see any bad data or anything like that. We spend a lot of time in there doing alignments. You can have that star tracker, but you got to make sure your telescope and star tracker are aligned. And so we spend a lot of time doing that. This is a theodolite. There's a collimator over here to the right that we use to do that. And we use our TV camera. The beauty of that, it works in the lab too. So when we want to line up on a simulated star source in the lab, we do it exactly the way we do it in flight using a TV camera. Saves a lot of time, actually. I always use the phrase, I'm not superstitious, but there are a few things I always do before any launch. Donuts are one of them. I can't actually eat them. I have high blood sugar, but there are always donuts when I launch. And if we have time at the end, I hope somebody will ask me how that came about, because it's one of my best stories. But I will not launch without donuts being there. And another thing, there's a place near Poker Flat, Alaska called Chattanooga Lodge, the only place you can eat for 35 miles. And this is a very remote 35 miles across a mountain pass. It's the only place you can go. And it's tradition to hang $1 up on the walls. And so on launch night, this is Justin right there, and that's Bill, and a student of mine, Shashwati. That's us, mounting the $1 right before we went off to go launch the rocket. This is a picture of the launch itself. It's a 2-stage rocket, so there's a 4-second first stage called a Terrier, and then a 60-second, what's called a sustainer, called a Black Brant. So this would be called a Terrier Black Brant that goes up. This is one kind of picture we can take. This is the cover I told you about, so when the rocket's on the launcher, we can move this cover over top, and then when we launch, we pull it away. Another one where you use a long exposure so you can see both stages at different times. This is taken from up on a hill. All the telemetry and the radar dishes and antennas are up on top of a hill, and we're actually about a mile away from the launcher. This is a member of my team up there also taking a picture. This was taken by a NASA photographer. I really love these kind of pictures. And there was an amateur photographer, not an amateur, professional photographer, probably about 5 miles away over at the Chattanooga Lodge, and took this picture with a long exposure. And you could see that we had some aurora that night. You can see some clouds in there, and you can see both stages of the rocket. I'm going to tell you about the data, but first I'll tell you about getting it back. It lands about 200 miles north of the launch facility, and we got amazingly lucky that it landed in a clearing. A lot of times they land in a forest with lots of trees. Sometimes the parachute is hanging in a tree. Sometimes they go in lake beds. All kinds of stuff happen. We found our rocket easy. It was in a clearing. There weren't any trees around except for this tiny little guy. And it's hard to see probably using zoom, but if you look really close, you can see that when it landed, the parachute dragged it. You can see trail in the snow where the parachute dragged the rocket for a ways. Think of the winds to do that. That's 1,100 pounds all put together, and you're pushing through the snow. But it went about 40 feet due to this parachute blowing in the wind. But that little tree stopped it. And what I'm saying may be hard to believe, but if you could see this picture up close, I promise you would see the trail. This is a picture of them digging it out. It took a month. We found it within a day, but there are rules. You can't have people out there working if the temperature is below -25. It can't be a high wind day, so that the helicopter can't fly. There's lots of stuff. The helicopters don't have enough fuel to go from Poker Flat up to here and back, so you have to have arrangements at different airports. It's a really hard thing to get it back. But I need it back because those mirrors are expensive. But it took them about a month to get it. And this is them. You can see, having been there a month, there was some snow on top of it. They dug it out, and then they pulled it out with a parachute. With a helicopter that you can see there. Just lift up the whole thing. Here's a better picture of it. Right here is they're coming in for a landing, not at Poker Flat, but where they went to get fuel. And this is a picture of it back at Poker Flat, where we did all the work. And so you can see it came back in pretty good shape. I actually have not laid my eyes on it. This launched January 27th. The day this picture was taken was about March 10th or something. I'm sorry, March 15th or something like that. So they had 2 guys up there to help bring it back, 2 guys from NASA, and they were going to pack it and ship it, but COVID hit. And so those guys came back without being able to finish. And so it sat up there until just about 2 weeks ago. And now it's at Wallops Flight Facility here in Virginia, but nobody can go into Wallops Flight Facility to put it in UPS and send it back to me. But I think that's going to happen in the next 2 weeks. So I haven't seen this yet. But as far as I can tell from pictures like this, it's looking pretty good. I want to spend a few minutes talking about the observations. This is a plot sort of what we got in terms of observation time. So this dark blue is the rocket altitude as a function of time. So it launches at t=0, gets up eventually to 260 kilometers. Our flight was perfect, exactly as planned. We got to where it wanted to be, and then it falls down like a rock. So it's just a nice sort of parabolic trajectory. We got ourselves pointed at 180 seconds. Justin nailed it first try. And so we got a good amount of time where this bright blue is time where we were looking at the star and pointed on it. But we're looking at high altitudes above where the nitric oxide is. And you can see that's actually from t=180 all the way to time about 350 seconds. It's a long time compared to the green, which is where we're looking at the altitudes we're interested in. You can say, Scott, why did you design it so you spend a little time looking where you're interested in and a lot of time looking above that? Well, you have to get some above that, and this is basically a rock being dropped at this altitude. You know, I can't control the speed of the rocket. It goes up, reaches 0 velocity, and then it hangs there and comes down at a very slow velocity. So no matter what you do, you have to spend a long time looking at the high altitudes and a relatively shorter time looking at the lower altitudes. And then eventually the atmosphere becomes thick enough, it's hard to point the rocket, and there's an altitude below which we can't see anymore, and everything closes back up and we come back in on a parachute. So all the action here is, you know, this is just, right, that's 100 seconds, right? So a couple minutes, right, is all this is. Everything has to happen really fast. So this getting aligned, you know, the motors only went off at about 100 seconds, and so by a minute later, we had everything set up and aligned. That's the time where the door has to open, the rocket has to check out the target star, then move to the guide star, then the target star, all that sort of stuff. This is what we see in flight, right? We're looking at a camera that's that's at the focal point of the spectrograph. So this x-axis is essentially wavelength. It crosses 4 nanometers, centered at 215 nanometers, and the y-axis is spatial. So if our pointing moved, this white line would go up or would go down. And that happened a little bit in flight. But this is the spectral dimension, and so you're essentially seeing the spectrum of the star, except this is the image at the focal plane, so it has some thickness to it. So here it is kind of zoomed in. It's not super clean. Even with that big mirror, there's not so much NO in the atmosphere that we get a really deep signal. So it's not, what we would call a high signal noise detection. But we see it. It's a nice, clean view. At this point, I want to say this is the third flight, which we had in 2020. We launched in 2011, and then we launched again in 2017. But I didn't tell you anything about that. In 2017, we saw this in flight. We got all lined up. Everything was perfect. And then the whole system turned off. The electronics failed, and we got nothing. I could tell you the brightness of the star because I saw it at the highest altitudes, but long before it got to the altitudes we were interested in, this all disappeared. And, like I said, there are some low points. That was January 2017, so it had been 6 years since our previous failure, only to get another failure. I can't describe how horrible that felt to see this and see it disappeared, or to see the look on Justin's face and Bill's face when that happened. But we did come back. We got this, and we got it in 2020. And so there's definitely a lesson in sticking to it. I won't spend a whole lot of time on the data. If we look at high altitudes where there's should be no nitric oxide, and we look at the transmission of the atmosphere, it's pretty much one perfectly as a function of wavelength, right? It's one plus or minus some noise. That's exactly what you want. There's no nitric oxide there. When you look at altitudes where there is nitric oxide, now you see an absorption profile. Yes, there's noise, but there's definitely nitric oxide there. And I won't go through all this data. This is the kind of thing I love spending time on. But this is the thing we're after, which is a profile of the nitric oxide density. Now, it's column density. Remember, I'm integrating through lots of altitudes. I'm integrating through the atmosphere tangentially. So this is how much nitric oxide we see along that whole path. But this is the measurement we're after. Yes, it's got error bars, but I know where the NO is, and I know to, not too bad of a precision how much of it's there. And I can do a calculation just trying a theoretical fit to how much volume density there is in nitric oxide, and then forward model that for column density, and it fits pretty well if I assume that the nitric oxide is peaked at 93 kilometers and has a density near 3. Those numbers themselves, would take a while to explain their significance, but it's something I spent 14 years trying to get those two numbers, and they certainly mean a lot to me. This is the thing we're after, but what I hope I did was show you what it's like to do this kind of astronomy from a rocket. It's not that uncommon. About 10 astronomers per year fly something like this. They look up, I look down, but I would say we all enjoy it quite a darn bit. I rambled on a little more than I thought I would, but I would love to take any questions you have.
That was great, Scott. Thanks so much.
Thank you.
I just want to make one comment as someone who has to sit and wait for objects to move far enough away from the horizon so we can look at them through our telescopes and show people something other than a little fuzzball. So I think it's fantastic that you guys were trying to do that.
Yes. Yes, and it's better than that. When you do it like this, you can't see the star from the ground. It's 10 degrees below the horizon for somebody on the ground, and just a little bit above the horizon from space. So you don't even get to, before launch, look out and say, is it there? You can't even do that.
That's really cool. Well, I would love to hear a little bit more about the context of those two numbers that you arrived at. What does it help you understand about potentially ozone depletion or whatever else?
Well, I do want to be a little careful. It's ozone destruction.
Destruction,
but when we talk about ozone depletion, we're usually talking about something that's more on a global scale. So I want to be careful to separate those two.
Thank you.
But so there's two things. So one, just how much NO can build up in the polar night. Now, we launched in 2020, January. We're at solar min, right? The sun is dead. So there's not much in the way of aurora right now. So when there's nearly nothing, just very low amounts of aurora all winter, we saw that much NO. That's a lot, right? So I mentioned the snowy mission that measured NO outside the polar region for 6 years. It got to 310 to the eighth. It got to the amount of NO we saw a handful of times, almost never. But that's one thing. So it says, even when there's a little bit of activity, you get a lot of NO because it had time to build up over the winter. And that's an estimate of the value, at least for that location. But the 93 kilometers is interesting to me too, because now you have time that region of the atmosphere had not seen the sun in 2 months. So there was very little in the way of destruction. Now things happen. The NO is moved around by winds. There's ways for some of the NO to sneak out of the polar region by being blown horizontally. So I don't want to oversimplify the picture too much, but where there's time for the NO to settle, where does it settle? We don't know that very well. It's settled at 93 kilometers. And that's probably saying something about the transport mechanisms, at least in that location. A rocket shot doesn't show you the whole Earth, right, like a satellite would. So I'm only learning about one region. But I'm learning about, okay, even with that 2 months, the NO was created probably at something like 110 kilometers. It traveled down about 20 kilometers to get to where we saw it. And that's telling us about how efficiently those transport mechanisms work. Now, I want to be clear. When I say something like that, there's a lot that goes into it. The winds are very special up in the polar region. You get the polar vortex. There's a lot going on. But now we have some information. Right, for the conditions of that rocket flight, we can see where the NO went, and we can study that with some simulations and make some sense of it. Does that help?
Yeah, it does. We had a question in the chat about how low the NO can actually go. Like, what's the lowest altitude it can actually traverse down to?
Well, if it gets down to where it reaches the ozone won't destroy it. But you'll lose some ozone as it reacts with ozone and then has to form the NO back. So we see NO at 50 kilometers, right? In fact, eventually it connects to NO that's created down near the Earth by lightning and things like that. So, in a sense, if there were a mechanism to move the NO, it can go to any altitude, right? But I don't think any of us think the wind systems or the diffusion processes have any efficiency to get it 250 kilometers, right? Somewhere around 60 or near there would probably be as far as it can go, maybe 50. But all those processes, the vertical descent, become a lot less efficient. Now, I did show you some particular events where the winds were very special after stratospheric warming in the polar vortex. Now, in those, you do see that descent, right? You see a lot more, and that does get to even below 50 kilometers. But that's rare and special and a whole topic to itself. Let me be careful, rare. It happens in almost half the years now. So it's occasional and special and something we're still trying to understand.
Awesome. Thanks for that. If anybody else has any questions, feel free to unmute yourself and ask Scott.
I saw the thing. Sounds like we need a teenager who is a gamer to work that problem.
Yeah.
True. Whenever I give tours of the lab and I explain that pointing system, because usually it's students, I'm giving a tour too, and I say, now look, who do you want to do this job? Me? I played one computer game in 1984, thought it was boring as heck, and never once tried it again. Or somebody your age, right, who plays with an Xbox and has skills and doesn't mind staying up late at night. Who's going to do it? But I tell that story a little less because Justin, who does this for me, when I first started telling that story, he was a student. Now he's in his 40s. So it doesn't make quite the same sense. But he does play with Xbox, so.
Well, I think my partner's son would be perfect. He's 16 and he games all night long, so he's your man. Sure.
Well, I did this myself when I was a student, and the principal scientist was a guy named Tom Woods. And he does totally different experiment. He's looking at the sun, but we needed to do a similar pointing thing because we had an instrument looking out the side. And I did it for him as a student. But after I stopped, he replaced me. He didn't have other students. He got his son to do it, and his son did it the first time at age 16.
Nice.
And kept doing it throughout college. So there's precedence for what you're talking about.
Cool. Somebody just asked about the funding for this study and how you convinced that organization or individuals to fund it.
Well, it's NASA. They're the only ones that would fund the sounding rocket, and they had to do all that support. And they have once a year a competitive thing. They select something like 5 rockets per year, although that changes year to year. With COVID, it's only going to be like 1 this year, but something like 5 per year. And what you have to do is convince them that the science is important enough, that we need that observation, and that you're going to learn enough to make it worth the money, and that you're really going to pull it off. I did that successfully in 2011. It got a little harder after we had that failure to convince them again that it was going to work, and then it happened again in 2017. But they understand, when I explained to them what all happened, and, I oversimplified the stories a bit for the sake of time, but I was a lot more detailed with them. They were understanding, and they too believed in this experiment. My friend Cora, who's listening now, she was a big part of helping explain the science and why this is important. They understood the importance of it. And I think one day we're going to do this from satellite, which is probably going to be something like $200 million to pull off something like that. But it's important enough to do it that way. And then we look at the whole polar cap and see what's going on in north and south and everywhere. I could talk a lot about ozone and what it does in the atmosphere. We think of it as protection from the UV, but it has a big effect on the circulation, the wind patterns, and things like that. So when nitric oxide alters that, the effects are very significant. So the importance is there to understand nitric oxide. There are good reasons to be doing this science, and that is what won it. And I should tell you too, Bill McClintock, who's my colleague, and he designed the optics for this, and I mentioned his name, he's a part of this. It's pretty much true. When you say Bill McClintock is involved in your experiment, they're going to believe it's going to work. Maybe it takes a couple tries, but they will believe it. He has received the highest awards NASA gives to citizens. He has an instrument today orbiting Mars, got 1 orbiting the Earth, got 1 studying the Sun. He led an instrument that went to Mercury. He did Jupiter. He is one of the most accomplished people out there. He's brilliant. He's a heck of a guy to work with, a lot of fun. And I'm just lucky that people like him and Justin and all those others I listed at the beginning want to work with us on this project. But it's people like that help convince everybody it's going to work.
That's really cool. Well, that's testament to how important your work is.
Well, I'm one of a bunch of people, but yes, thank you.
Any other questions for Scott? So somebody in the chat just asked about the donuts.
Oh, okay. Let me apologize ahead. I can't tell the story in under 2 minutes.
That's all right.
If you have 5, I mean, I think this is one of my better stories.
Let's hear it.
This goes back to the 2011 flight. I'd flown a bunch of rockets, but 2011 was the first time I had the lead role. And we were at the Chattanooga Lodge where I showed you the picture. And I used to live in Alaska, and I'd flown a lot of rockets out of there. So I knew my way around. I knew the Chattanooga Lodge, and I knew the people who ran it. And I was there with some other people from the rocket. And I was saying that, come launch night, I want to do something really special, right? I want, after everybody leaves here, to say, I want to work on Bailey's rockets. I want to be on his projects, right? I want to be known that way. So how can I make the launch special so that everybody wants to be a part of it? And the owner of the Chattanooga Lodge was there, and he's a great guy. He's been doing this. He's been amateur astronomer for Aurora for 50 years. He's there, and he says, Scott, I got you covered. Nobody knows this about this lodge, right? But we make the world's best egg rolls, okay? You come here the night before the launch, I'll make you some egg rolls, and they will be talking about how good those egg rolls are for years. I promise you. And I'm like, that's it. Right? Nobody would ever think of that. And nobody thinks of Chattanooga Lodge for their egg rolls, right? It's perfect. I'll do it. So I said, okay, egg rolls for 40, right? January 26th, 2011. I'm going to send somebody over here. And he says, fine. And so come launch night, as we're getting set up, and remember, we had to be there way earlier. So I sent somebody over to Chattanooga Lodge to pick up the egg rolls. And I hand him $100 in cash to pay for them. I had never talked money with those guys. I just said egg rolls for 40, and I assumed $100 was going to cover it. Well, he comes back and he hands me the $100, and I say, well, what's going on? Where's the change? And he goes, there is no change. And I said, what do you mean? Did you get the egg rolls? He goes, yeah, I got the egg rolls. I delivered them to the guys. And I said, what's going on? He goes, and he hands me the receipt, $842, right, for those egg rolls, right? Way beyond anything I had thought, right? Considered, how am I ever going to get the university to reimburse me for $840 worth of egg rolls? because I want to be the most famous researcher that those guys work with, right? And I'm thinking, holy crap. But anyway, we had the launch, so I get that out of my head. So this was the first night of launch window, the first night we're going to go. And I'm different than most, right? I pick a day and say the geometry is going to be right. Let's launch that day. And I know it a year ahead of time. A lot of people wait for conditions and all that sort of stuff. Well, anyway, that first night we get close to the launch and NASA canceled it. They say not to do it. And so we're way up on the hill where the telemetry is and the radars are. We don't know why they do it. So we get in a car and we head down to the launch facility and ask them, why it was canceled, what happened. It was a weather thing. The snow was going to come the next day and cover up the parachute, and they were worried they couldn't find the rocket. So had a good reason, but I didn't know. And so we drive down the mountain, we head to the blockhouse, which is where the launcher is. And you have to remember the perspective of the guys who work here. They came up, for a January 20 launch. They left a day or two after Christmas. They left their families. They gave up half their Christmas break. Most people take off that next week, but they came up to Alaska to do all this work. They've been all working in tight quarters for a month, and this was supposed to be the night it's all over, right? Here comes me and Bill walking up to the blockhouse, and here comes one of the electrical technicians coming out, and he's just storming out. You could see on his face, that he's just angry, he's upset, and just as mad as could be. And this particular guy was a legend in the field. He's been on all kinds of rockets, done all kinds of things. He's famous, and just angry. And we're like, what's going on? He goes, this is your fault. This is totally your fault. And I'm like, dude, I don't even know why they canceled. I came here to find out why it's canceled. I don't know any more than you do. I don't know what's going on. He goes, nobody brings egg rolls to a rocket launch. You upset the gods. Nobody does this, damn it. Right? You bring donuts. You bring donuts to a rocket launch. Nobody would bring egg rolls. And then he stormed away. And he was totally serious. This is a guy I had known 20 years at that point. He was totally serious. He wasn't joking, right? The egg rolls had him that mad. And so ever since, in honor of that guy, it's donuts.
But were the egg rolls worth it? Were they that good?
There was not a crumb left of those egg rolls that night. Not a crumb. But it turned out we had some trouble. We had to scrub 4 nights after that. And I bought donuts every night. In fact, every night since then where we were going to do a launch, I brought donuts every single time. But after 5 days of scrub missions, every corner of every building, every place somebody worked, there was a box of half-eaten stale donuts. You couldn't go anywhere and there wasn't leftover nasty donuts sitting there, right? So the egg rolls were totally much more popular than the donuts, but I was told it had to be donuts, and I'm never going to back off. Another funny thing was that one of the people who worked at the range, she grew up in Korea, and she made some pretty mean egg rolls herself. So after a couple of nights of the donuts, she started bringing her own egg rolls, so we did get them back. Maybe that's one of the reasons nobody ever finished the donuts after that, but they made sure I brought them.
That's a great story. Thanks for sharing.
Sure.
Well, I don't know if we can end on a better note than that. That was great.
I appreciate you guys listen to me. I know sometimes I get into my own thing, but I appreciate you being patient with me.
Oh, that was a lot of fun. So we do have some door prizes and a raffle prize. So everyone who is here logged in is entered for the door prizes. And Scott, if you wouldn't mind unsharing your screen, I'll share mine and just show people what the door prizes are. So we've got these cool stickers designed by some local artists here in Jackson. They call their business Holly Sage Art, and they designed some cool stickers for the eclipse a few years ago. So we've got the Chasing Totality sticker, the Jackson Hole Eclipse sticker, and the Wyoming Eclipse sticker there. So we've got those 3 stickers. And then, as always, we've got a print from one of our board members, Mike Adler, who does really amazing astrophotography. Mike's got an incredible observatory at his house, and a pretty amazing camera system that he uses to take pictures of deep space objects. And so we've got some framed glass-covered prints that Mike's generously donated that we're going to raffle off as well. So one print for one of the door prizes, and then a print for a raffle prize. But we'll do the stickers first, and then we'll do the grand prize for the door prize, one of the prints, and the raffle as well. So we'll do the Chasing Totality sticker first. And the winner of the Chasing Totality sticker is Ian Edwards. All right, so now we're going to do the Teton Eclipse sticker. Deb Wersch. And then lastly, for the Wyoming Eclipse sticker, Liz Mosley. All right, and now for one of the framed prints. Let me show you which one it's going to be. We've got a lot of these in the office, but I think we'll do, this is the Elephant Head Nebula. I think we've got one of these in the shop. So the winner of this framed print for one of the door prizes is Deborah Brand. Nice work, Deb. All right, and then, yeah. All right, so then for those people who actually bought raffle tickets, we're gonna draw one more for another framed print. And we've got J.R. Dalby. He's the lucky winner again. J.R. bought 20 raffle tickets during the last event, so he's got a lot of tickets in the bin. And he bought 5 more tonight. Congrats everybody on your prizes. You can pick those up at the Wyoming Stargazing office sometime next week. We're there usually from around 10 a.m. onwards. Again, thanks so much for being here tonight. Scott, thank you again for a wonderful presentation. We've got another Science Speaker Series event with Dr. T.S. Kelso, also having to do with space flight. That's going to be on Saturday, August 8th, a week from tomorrow. And then we've got another one planned for September as well, which we'll get up on the website in just a little bit. So if you like these events, tune in just about a week for the next one, and again in September. We also have a lot of other online events that you can join on a more weekly basis. We've got our virtual public stargazing programs. The next one of those is going to be on Saturday, August. What date is that going to be? Saturday, August 15th is going to be the next one. That's the next Saturday around the new moon. We've also got mind-bending astronomy, in which I tackle a crazy astronomy topic and try to make sense of it for you. We post those on our YouTube channel. We've also got Sci-Fi Explained. Every other week, I dissect a sci-fi movie for the parts of it that are true to science and the parts that are science fiction. And then Looking Up. Looking Up is a podcast where I share some astronomical facts, some history, and current events of stuff you can see in the night sky. So yeah, we're trying to boost our online presence. So check out our YouTube channel. If you have time to subscribe to that, we'd really appreciate it. The subscription is free, but it just helps us build momentum to get this content out to more and more people. And then I also wanted to make a shout out for Old Bill's Fun Run. The Old Bill's Fun Run giving period begins tomorrow. It's a huge community fundraising event here in Jackson, and Wyoming Stargazing gets a match on all the donations we receive beginning tomorrow through the second week of September. We're a 501c nonprofit organization, and this fundraising event is our biggest each year, and it helps us provide all of this type of programming for you. So I'll put the link for that in the chat, and if you have a moment to make a donation at some point, we would incredibly appreciate it. If I can just find the chat. There it is. And put that link in there for everybody. That takes you right to the website where you can make a donation. But again, thank you all for being here. Scott, thank you. And I hope everybody has a wonderful evening.
Thanks, Sam. Thanks, Scott.
Thank you.
Thanks. Thanks.
Thank you, Deb.
Sam?
Hi, Mom.
Hi, I put something in the chat, but you didn't see it.
Oh, I didn't see it. What did you say?
I said, when Dr. Bailey's research is all finalized, is there any chance it would help the polar bears survive?
No, it'd be very atypical for this NO to get down to do anything to do with the surface. Winds and climate can change somewhat, due to the ozone effects. Not the NO, and the NO is toxic, by the way. So wouldn't be good for anybody to breathe it.
You couldn't detoxify it?
You wouldn't have very long if you were breathing any appreciable.
I know. Well, I see. I get it. Got it.
Well, any last questions or comments before we wrap up?
Yeah, Sam, so almost back to the beginning. What is the relevance of the NO? I see the title of the talk is the mesospheric clouds. So
Yeah.
please put A and B together for me.
They're not related to the clouds. It's a topic on its own. I do research in polar mesospheric clouds, but it's a separate topic.
Oh, okay.
So that was a mistake I must have made in exchanging emails. So I apologize to however I did that.
Or we made, I don't know.
Because when I got the email, we had just flown this rocket. I had just assumed that's what people wanted to hear about. But in some sense, the clouds are more my bread and butter than this is. But I don't know.
But so what is the relevance
Of the clouds or the nitric oxide?
of the nitric oxide?
It's actually important for a bunch of reasons, but one of the key ones is it affects ozone. And the way it affects ozone happens in a way that can change the circulation of really the entire atmosphere.
Well, that's a good beginning. So can we have another talk? Or 5 minutes?
Yeah, I'm happy to keep going. Ozone, I'm sorry?
It's up to Sam.
Well, totally up to you, Scott. We've already had a lot of your time. I really appreciate it. But if you got 5 minutes, that'd be great.
Yeah, let me take 5 just because it's important to explain. Since your tax dollars pay for this, that it was worthwhile. The nitric oxide by itself, if it just stayed in the upper atmosphere and did nothing, then it's just something interesting. But there are things it does, and one of the key things is it's a destroyer of ozone. It's a catalytic destroyer of ozone. So a small amount of nitric oxide can destroy a lot of ozone. And, we have ozone is important because it protects us from solar UV, but it does a lot of other things. Ozone is actually crucial to the wind system in the upper atmosphere. And that's because it's crucial to the overall temperature of the upper atmosphere. Ozone is actually a greenhouse gas. It doesn't get much press for being a greenhouse gas, but it is. And it's an important one. And so the way it radiates, we think of greenhouse gases as warming the atmosphere, but when you're up high, they cool it, right? The way they warm it is by high altitudes radiating energy, and some of that energy gets picked up at the surface of the Earth. So the upper atmosphere gets colder. If we destroy ozone, right, then we stop that process. And by changing the radiation at a particular altitude, we then change the wind system, because winds are just basically either pressure or temperature differences in the wind the air trying to move from one place to the other to correct that. You destroy ozone, you change the circulation of the atmosphere, you change the pattern of the weather very significantly up high. and sometimes significantly down low. The polar vortex, when we get all that cold air, is not due to nitric oxide, but it is due to changes in the upper atmospheric winds. Changes in the jet stream are all the kinds of things that ozone can influence. And so if that nitric oxide created by the aurora ultimately destroys ozone, it will change the wind patterns and have an impact certainly on the local climate and possibly on the global climate.
Okay.
Does that help?
So does this go, yeah, definitely. So does this go back to the Earth's magnetic field issues or the solar radiation issues?
Both to a degree, but mostly the particles in the solar wind. So those particles that created nitric oxide started on the sun and then took a complicated path around the Earth's magnetosphere and ultimately into the polar regions.
Right.
And ultimately to create nitric oxide. So it very much connects to the sun.
So it's not something we have, we're creating or in control of. It's
correct. This is all.
It's solar system.
But there is something. You know, I showed you that there were these unique events where the nitric oxide got pulled down to really low altitudes.
Yes.
We've only been seeing that in recent years. Now it's possible the observations were not good enough in years prior. But we had some observations, and there's evidence that it probably was not happened to the same degree 20, 30 years ago that it is now. And so climate change could be affecting the atmosphere in ways that promote this descent of nitric oxide. We don't know that, we don't understand it, but it could be happening. But mostly these are natural processes we're looking at that may be influenced or gaining more importance because of human-induced changes in the atmosphere.
Mm-hmm. 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 Okay, thank you.
Sure, thank you. I appreciate your interest. And that question you answer is the hard question we all have to be able to answer. If I can't explain to you why this is important, you shouldn't let your tax dollars pay for it.
Well, it looked like a fun experiment and a fun launch. But the question is why?
No, I'm glad you asked, and I hope you came away thinking it was worth it. But
yeah,
a lot of fun.
absolutely,
yeah. I'm not sure. I think I lost a few years of my life from those heartaches we took along the way, but I gained back some of it by the fun we had of the success. And I'll tell you, there was some happy tears that night when we saw it work.
Yeah.
And still happy tears. You know, we just, that plot where I showed you the results, we only got to where we could make a figure like that a couple of weeks ago.
Oh,
and
wow.
I had tears in my eyes then.
So the timing was just right.
Yeah, it was perfect. Not to mention it, a couple of weeks ago, I was thinking maybe I should give a talk on the clouds because I'm much more ready for that. But I didn't know.
Well, I'm glad it all worked out. And I'm super excited for you, Scott, that you got those fantastic results. And thank you again for being here to share those with us.
All right, well, thank you. I really appreciate your interest and for you guys giving me this opportunity. I had a great time with it. Wonderful. I know I rambled some, but I appreciate your patience with me.
Oh, it was great. I really enjoyed it. Thanks again. Have a great night.
All right, you guys too. Thank you and take care.
Yeah, take care.
Thank you.
Take care.
Thanks.
Bye.
Bye. Bye, Mom. Bye, Sam.
Bye.
Bye, Deb.
Bye, Mom.